before I kick off, I'm very grateful to be speaking in front of a... Can you hear me okay, or am I not? All right, because I'm going to kill my neck trying to talk like that. But anyways, I'm really grateful to be speaking in front of circular tables. I'm getting married in a couple months, and this is going to be great, great transition. Awesome. So this talk is going to present our new paper on querying databases with function calling. So I hope this will inspire you to check out the paper. And I kind of want to start off by diving in with the thesis of like what I'm trying to argue with this talk. So first of all, I think MCP, let me also do a quick show of hands. Does everyone here know what MCP is? All right, awesome. So I think it's awesome. We finally have a way to say, hey, what are the tool definitions for your software? The standardized way of defining the environments, deploying the tools separately from the runtime of the LLM. All that is awesome. But it will not work unless you have some type of natural language to API layer on top of your software. If you have, probably you have complex arguments for your software. And so this is gonna show how you can use the Gorilla LLM framework to evaluate this and understand the state of trying to just do function calling with really complex arguments, and that it doesn't work that well. Okay, so a bit of context for why we did this. So there's this whole thing about connecting LLMs to external context. The LLM is trained on language modeling the internet. It can only get so far without these external tools and continuously updating private data, blah, blah. So the most common example has been, so we have search engines and then we have text to SQL. So search engines, they give us context like, say things you would expect from a keyword index, like lobster mac and cheese, get me dishes that are exactly that. And then there's the kind of canonical vector search example where you say wines that pair with seafood pasta. And because, say, Chardonnay, Pinot, I don't actually know what wines pair with seafood pasta, but these kind of wines, they don't have any keyword overlap with this query, so you use vector search. But then you also have information that's in text to SQL. So if you say, these calculations, a database is like a big calculator. You're saying, what's the average price of lobster mac and cheese in Boston? Does this filter on in Boston, lobster mac and cheese, and then average price aggregation. Or you say, what did I order from Uber Eats? So a RAG, like a RAG built with vector search or just a search engine will not tell you exactly what you ordered from Uber Eats last week, like everything you ordered. It will give you like the top 5 results of what's relevant to that query. So we want to have both of these things because, yeah. And then there are some examples of overlap where you might have, lobster mac and cheese in Boston group by neighborhood. So it's like a search engine query that still kind of does this like SQL style like filtering and then like group by transformation of the result. And then you also have these things where you're doing symbolic aggregations over like vector search engine style queries. So you say like lobster mac and cheese, and then you're doing some type of computation on the result. So there's like some overlap between these two things. And so other people are kind of noticing this. They're saying, people are studying textual retrieval and then relational retrieval as just like two entirely separate things, but we're arguing that it's not this idea that the search engine is like decoupled from the database. We think these things should be merged, and we have the, of course, vector database, we merge these things. Okay, so then the other thing is like we had this vanilla RAG where you had this hard-coded, prompt, retrieve, give the context to generate. And then we have this function calling, which is like, I like to call it like the Turing complete agentic architecture. It's like, the superset, it can simulate any other agentic architecture because it does this sort of like, iterative function call and reason steps. So we want to see how well this can just use, this complex database querying as its tool that it's making the calls to. And so we did a lot of work around, agentic RAG and, pivoting into this. And then there's, so now we're starting like, how does this work more technically? And this connects to the MCP thing. You define a tool definition. So most of these tools are like really simple. It's like you're getting the weather. And so the only input argument to it is the zip code of the city you want the weather in. So what we can do, and I couldn't fit this on a slide nicely, but we're now trying to introduce a complex tool for querying databases. So it has an argument to search query, integer property filter, text property filter, Boolean property filter, aggregations, group by. And so kind of the key to this is that you have this like optional argument thing. So, that's like just how you're typing it. And so this is like the tool definition that we present. And this was kind of before MCP. Now you'd call this like an MCP API. Like this would be one of the MCP tools that'd be like in your MCP thing. Cool, so now what this looks like is instead of writing SQL queries, the natural language is translating it into these function calling arguments. And so, it could be simple, it could be just one argument, or it could be these two arguments, or it could be, 3 arguments, or however many. And so a reason why you can do this is because we now have this structured outputs thing. And so there already was kind of structured outputs in place where the LLM would generate, and then it would validate against a schema, and then it would have like a retry prompt. That was like the first iteration of this. But now what we have is these, and this is ChatGPT generated, don't try to like learn from this, but we have these, we have these finite state machines, which is how they're sampling the tokens such that it is only possible to follow the schema. Okay, so now we have the model context protocol. So I think the key innovation is that now you're writing out your tools for your software, you're making it really easy to deploy them in a separate runtime from the LLM, you're isolating the dependencies of your software with the LLM runtime, and all that is super awesome. And then you have the UI layer with Cursor, Anthropic Desktop, Windsurf, all those things. Okay, so, but people are still with these MCPs. This is my friend Ian, who's working on bio MCP, making it easy to access clinical trial data, genomic variants, and so I even truncated this, but the tools are like these massive tool definitions. So that's kind of what I'm going to prove is that this won't work. If you have like a lot of arguments, the LLM won't be able to navigate these arguments. So unless you have natural language to your APIs layer on top of your MCP, which is what we've built at Weaviate, we built this thing called the query agent, which is like, like our text SQL layer. Like most database companies have something like this now, but so this would be like my proposal to how you would solve this is you need to have your sort of natural language to my APIs layer on top of your MCP. Okay, so thanks to structured outputs, our agents can reliably format these complex tool calls because before you couldn't even make it that far, but still it's not like choosing the correct tools. So, and I'm really happy to be citing Joe Burgum in this talk. Does anybody know who Joe Burgum is? Awesome. Also, I'm always really happy when we agree on something, and so he's recently been tweeting about this exact idea of we have 20 plus tools. Let's say, it's my MCP, your MCP, and each one has like 8 arguments, 5 arguments, 3 arguments. The LLM just isn't going to be able to navigate all these, tools and the correct arguments. Okay, so the way to sort of understand this is, I think, by following the Gorilla LLM paper. So this is a really great paper early on, I think like 2023 even, about connecting LLMs to APIs with function calling. I think at the beginning it wasn't even clear that function calling was going to be here to stay, and I think the way this group has just like continued to push function calling, the Berkeley function calling leaderboard, and all sorts of things like this, I think have been really awesome. Okay, so now we have the Weaviate Gorilla, and get ready for the ChatGPT Gorillas. So the idea is, LLMs plus Weaviate APIs, Weaviate Gorilla. So the first technical thing from the Gorilla paper is abstract syntax tree scoring. So if you're just going to be doing exact match, we did end up doing exact match because if you're trying to communicate this to like, marketing, like you're trying to communicate this more broadly in like the software market sort of, it makes more sense to explain an exact match score than like abstract syntax tree score. But abstract syntax tree score is like the partial match of the API call. So, it's a more technical way of understanding where it's at. So what that means for database queries is, say it selected the right collection, menus, but it used a search query, and then say it didn't use a filter or use group by. So it's like partial scoring, basically, is all that is. Okay, so then self-instruct data generation. So this is kind of the second part of the sort of recipe of this. Also, abstract syntax tree is the metric. Really, the recipe to this is creating the data set where you're simulating your tool calls by generating natural language commands for when you would want to use each of your API arguments. So you generate one natural language command for each of the API arguments that you have, and then you have a data set of natural language commands to then evaluate the model with. So for database queries, we could, similarly to like this weather example where you're just saying like, what's an example of when you would use this get weather function? What is weather in Boston? You could do that for the database APIs too. If you just say, write a query that would need an integer property filter, it would just, it could do something like that. But the database querying problem is like super particular to having a particular set of schemas. So we also integrated that instead of doing this kind of like more open-ended, just generate a natural language command for when you would want to use the API. Okay, so this is one of my favorite gorillas, maybe my second favorite. So we create these synthetic database schemas, and I think like the depth of this is just insane. But you have like, so this is just a simple example where you say have 3 collections. We could go all sorts, we could go down the rabbit hole of data models and all that kind of stuff, but you're saying that you have one property that is that has a search index on it, and the rest of them are kind of like normal properties. Like party size would be like, so like B plus tree index on that one. But aside from that, it's like about you would usually like filter with these other properties, and you'd have search queries. And so that's the idea: is we manually create these schemas. But so some future work that we're doing is scaling this up. So something that we've built at Weaviate is called the transform agent, and it's basically like batch LLM inference over your data. And so we're on one end saying, how do we show people what you can do with this? And on the other end, we're continuing our research into database querying. And so there's this data set called Persona Hub, and Persona Hub are these personas derived from internet text. And so there's 1 billion of them, and so a subset of them, which is still actually the world's largest text SQL data set. You only need to beat like 100,000 is the goalpost for that. But we generate synthetic schemas and queries for personas. This is like some future work on how we're scaling up our natural language to database querying research. Okay, so anyway, so back to this paper is we manually designed these schemas. We generate one natural language command for each of the combinatorics of, say, using a search query with an integer property filter with a Boolean aggregation, grouping it by some property. So we go through the whole combinatorics of that for each of the sets of 3 schemas. Okay, then also we just have this data annotation UI just to make sure that it looks okay. Okay, so now here are the results that we found. So this is kind of the argument of saying this won't really work that well. We find 74% exact match for Cloud Sonnet, and I think it's definitely worth mentioning that these are like super targeted queries. You think it would be really easy to pick it out because of how like direct it is on being synthesized to target the particular combination of filters, but it still isn't able to navigate it. And then as you get worse models, it's gonna get worse and worse. So maybe that's also part of Anthropic's like strategy with MCP, is that they're the best at this. If you try to swipe them out with some other, less expensive, running on your own infrastructure type of model, then you're in trouble. So that's kind of the state of this that we found. And then, so we make these radar plots to kind of break it down by the particular, how good is it at search queries versus text filters, and we find that it's really bad at differentiating between search queries and text filters particularly. Okay, but I meant for this slide to be after that other slide, but this is probably the more important thing, is understanding like the maintenance cost of having benchmarks like this. So we manually curated this data set to be 315 queries so that it only costs us $8 to, exactly $8, to like rerun this every month or so to just keep up with what is the state of function calling with all these different models. Okay. All right, so I don't think it's terribly interesting, but we break it down by, we have that restaurant case that I showed you. We also did a similar thing for health clinics, courses, travel planning, visual art, just designing synthetic schemas, queries for these schemas, and seeing how well this works. So then another thing to note is a lot of these models, with the function calling setup, they just like outright don't choose to call function at all, which obviously hurts their performance on the benchmark because they're being evaluated on how well they do the correct function calling in like a one-step function call. Okay, so then some of the kind of other things we looked into, probably the most important thing is this last thing of structure generation. So instead of defining your tool as a JSON and giving it to the function calling SDK that the model providers offer, you could also just like type it as a Pydantic base model and just have it be a structured output. So the reason that thing is important is because it's important to understand if the big language model providers like Anthropic, OpenAI, if they're fine-tuning with this function calling syntax, and if that's resulting in this being like a superior way to integrate LLMs with tool calls because of just like the particular formatting of it and it being aligned with that. So we find that that's not the case, but I'd say it's super important to keep an eye on that, especially as the function calling sequences get longer. This is just one step, one input, one function call. But in the future, you probably have like 5+ function calls. It's doing that like agentic, doing several things, getting back the response. And so it's interesting to see if that particular format of appending the results of tool calls as like a message. If you've seen like the user message, tool call message, this like dictionary type of way of doing it. If the models will become fine-tuned for that particular kind of formatting of the data. Okay, so our key takeaways from this study was that they're great at utilizing Boolean properties, which is interesting maybe for thinking about how you design your schema. If you can maybe, and then coming back to the Weave transform agent, and if you can derive like a Boolean property from your data, then the LLMs are going to be great at using that Boolean property. So it has some implications for how you're designing your data schemas. And then we do see significant variance across the different schemas, so the sort of semantics of the schema, but probably there's future work on describing the schema to the model, describing the data that's in it, and how that will go, and all that kind of stuff. Okay, so all right, so here are some kind of like low-hanging fruits of what's next with this. Probably like an obvious one is instead of, so right now what you do is mostly you just define all your tools and you give them all the model, and you have this kind of like function calling SDK. This is like the most common way that people are building these kind of systems. But this kind of like retrieve the particular tools for a task, that's a cool idea. Another one is retrieving the docs for the tool. So this is something that comes from the original Gorilla paper, is that you only have 1,024 tokens to describe your tool. So you can't really like tell it too much about like what a text filter is, even though hopefully and who knows what your particular software, what the arguments of that are. Querying databases is obviously something that's like pretty general. But so you can't really describe your tool that well to the model. So maybe you retrieve the tools that you want to see, you retrieve the docs for tool, and this kind of becomes like a part of the MCP story. Okay, so then another thing is this kind of like predicted views. So this is like with text to SQL models, you have this like schema linking thing. It's like one of the things when we publish this is people are asking, oh, but this doesn't support joins. And so that's because relational databases are usually designed to have fragmented tables so that you don't, the reason being that you don't duplicate the data, but then when you query, you need to like join these things together. So you have all these this query plan stuff, and I think that there is a good chance that the LLMs just like take on a lot of that query planning stuff, and that kind of like cardinality estimation is like something that goes into the prompt, and it doesn't need to join the tables. It can like duplicate data, but move it to cloud storage. So we see all this like separation of storage and compute architectures for database systems. And so I think we'll see a different way of schema linking emerging with LLM database query. Okay, so then the next thing is like about agents versus compound AI systems. So this is like a preview into how our query agent works. We don't use like a function calling loop for our natural language to APIs product. We instead decompose it into the steps, which is like probably what you will do. That's probably more what I'd expect people who like attend a conference like this to be doing. If you're building agentic systems, you probably break it into a series of inferences that you know in advance rather than just using this like wildly open-ended agent thing. But this is definitely like the more common thing for people to be doing. Okay, so then the question is maybe like what does optimizing it, what does now trying to get it to the next level of like trying to take our 74% to 100%, and we're trying to do it for Llama 3, or I guess now, well, not that one, because it's like mixture of experts, still terribly complicated to scale that one, but like, say you're trying to get it to, smaller model, 100%. So the first thing to do would be the agent prompt as it uses the tool. So you're not optimizing the tool description itself, you're optimizing the agent prompt as it's using the tool. And so you could either set up a train test split and use, say, DSPy for this, or Letta is a very interesting idea. I know these might sound like, if you're familiar with these things, they might sound like really different technologies, but Letta has this kind of like, meta memory updating. So as it's using the tool, it will update its own context window about like what the tool is, what it's learned from using the tool. And you can think of that as a form of prompt optimization. And then you have like enhancing the tool descriptions themselves, but again, the tools with these SDKs are limited to 1,024 tokens. So I don't really think you get that far doing that. And the next thing would be so similar to this thing, but you'd have like reinforcement learning on the agent using the tool. This is kind of like DeepSeek R1 for like search is mostly what we're seeing now. But again, if you're only searching, you're really missing out on what the database can do for you, because it can search with filters, it can do these aggregations on the results and all sorts of things. So just kind of like searching alone probably is enough. Okay, and then the thing that I'm really excited to talk about, and so I tried not to like, BS you all too much and like keep this more into like what we've done concretely, but this is kind of like this future direction thing that we think is just super exciting, is going deeper into pre-training with these like LLM systems that use databases. Okay, so you've probably heard of these emerging foundation models for obviously the multimodal thing, vision, audio, language all in one model, Probably heard of video, robotics, biology. Awesome. So I hope to inspire you to think about like what does a foundation model for agentic databases look like. And so this talk has maybe been a limited view of that. Again, not BSing you too much in this talk. It's just like concretely what we've done. We've built this system that queries databases. But where we're hoping to go is agents that do data engineering tasks. It's actually also something that we have released is like a batch inference that does a lot of data engineering tasks. But now you're going to have your database will do data engineering for you. It will help you with like LLM as DBA, and thinking about like the state of a database as an input that is similar to like not just language, like because a database has a state about, you know, it's got this LSM segments, it's got these different indexes, it's got some understanding of the workload that it's seeing. And so that's what we're aspiring towards, is building these totally new models that can control these totally new agentic databases. Awesome, so kind of concluding, Weaviate. So what Weaviate is it started out as a vector database, all sorts of awesome things. I think so much goes into, this is kind of the way that we explain Weaviate, is that, you know, at the core we have this open source vector database that, you know, supports all the things, multi-vector, acorn filtered search, quantization, all that awesome stuff, hybrid search. And then probably, you know, this part is really underrated, is all the work that goes into like enterprise cloud, bring your own cloud, like super talented people working on that kind of stuff. And then this is sort of and then so, you know, a lot of looking at the ecosystem and how people are using vector databases, or like how people are building RAG systems. And that's where we saw a lot of this function calling stuff, is particularly looking at these LLM frameworks. And that's kind of mostly what you'll see if you're trying to build your own compound AI system, or you could probably argue that now in the current state, all of the LLM providers are like frameworks because they offer you this function calling SDK, they offer you all sorts of things, so they're kind of like becoming one with that. And then now we've launched this new kind of agents layer where we have the query agent that's mentioned, the transformation agent, which does this like batch inference over your data and saves it back into the database. So say you have a collection of you know, your customer descriptions, and you want to say, and you have some sort of new product, and you want to go through all the customers and say, you know, rate on a scale of 1 to 5 how interested you think they would be in this product. This lets you like scale it up. We have like, you know, GPU infrastructure to run this inference really fast and compute that. And then we do this personalization agent, which is like similar to the query agent, but, you know, doing like recommendation system stuff. Okay, awesome. So I'm not going to ask you to follow me on social media, but I would really appreciate it if you could tell me which one of these gorillas you think is most interesting. Like,